The cantilever spring design example is the nominal the best problem. So we would like to use two-stage optimization process to first optimize SN and also maintain the mean output at the target. Here we can use a very simple concept to represent why do we need two-stage optimization for nominal the best problem. Assume you are Robin Hood. You should be very good at the archery. So when you shoot arrows, you would like to right at the target for every shoot, not the average. So this is a cartoon to stand for the condition. Here you want to shoot 6 arrows to eat a poor servant's apples at the top of his head. Unfortunately, all these 6 arrows scatters. Although you might argue the average is right at the apple, but this is no good. So in the first stage, we are using SN ratio to be the objective, so we can obtain a design where the average loss will be the smallest. The average loss stands for the mean output to the target square plus the standard deviation square. And after the first stage optimization, you do minimize the average quality loss. But this is kind of a condition that you minimize your error into a single point. However, this single point is not really at the target apple, but at somewhere else. If you are the servant, you will not be very happy. So Taguchi method suggests we should always move the average output to the target here for nominal the best problem. This is the process two-stage optimization he proposed for nominal the best problem. At the first stage, we maximize SN. Therefore, we can obtain a design with the smallest sensitivity, performance sensitivity to noise factors. But at the second stage, we should try to move our average to the target. So he suggests we should find a factor which is called scaling factor from a type 3 control factors. Then we can use that scaling factor to adjust it in order to obtain a mean output at the target. And I'm using this figure to represent this concept two-stage optimization process. At the first step, we maximize SN so we can reduce variability. Like initial design over here, and this is our design target. From our first step, optimization, we maximize SN. Therefore, this design will come to some place B. And in the second stage, we would like to move our average to the target here. But when we move the design to the target, we still want to maintain our achievement from the first stage, where the SN ratio has been maximized. How can we do that? As I discussed in the previous slides, he suggests using a scaling factor, which is a control factor from type 3. Let's refresh the concept how to classify control factors into 4 categories. And we are classify these control factors according to their reference to mean output and SN ratio. Type 3 control factors has an effect on mean output, however, doesn't have an effect on the SN ratio, which means that if you move your type 3 factor, the SN ratio will pretty much remain the same result. However, the mean output will shift. So that is the reason why we should select a scaling factor from the type 3 control factors and then use that scaling factor to move our average output to target. And during the adjustment, we don't need to worry about the SN since type 3 factors doesn't have an influence or have very small influence on SN. So we can maintain our achievement in SN when we adjust the mean output. So in summary, the two-stage optimizations following this process. First, we assume the interaction effects are negligible, so we can determine the best level for each control factors. Then we classify our control factors according to their influence on mean output and SN ratio. So from the type 3 control factors, we select a scaling factor, which will be used in the second stage optimization. Since in type 1 and type 2 control factors, they will have influence on SN, we shall select the level where SN will be higher. But for type 3 and type 4 control factors, since they have small influence or no influence on SN, if we have the cost information for each level, instead of choosing a level where SN can only increase by a small proportion, it's better off to choose a level where the cost will be smaller. And after that, the only factor need to be determined is the scaling factor. So we move the scaling factor up and down to move our average output to target. Let me use the cantilever beam spring design as an example. This is the effect plot for mean output and SN. For control factor B, it has an influence on mean output. However, for SN, it's pretty flat, which means that they have a small influence on SN, therefore make it a perfect type 3 factor. As you can see, factor H has an influence on both mean and also the SN, so it should be a type 1 control factor. For L and E, since they have no influence on SN and some influence on mean output, therefore they are also type 3 control factors. So we should select a scaling factor from the type 3 control factors. We have 3 candidates: the width B, length L, and also the material property E. As we mentioned before, we need to adjust these scaling factors, maybe up and down and freely, in order to move our average output to target. Here, material property E, which is a Young's modulus, is not an easy property you can adjust. So Young's modulus is a discrete variable. It is not suitable to be a scaling factor. And now we have 2 factors to select from, length L and width B. You can select by yourself, but if you still have some cost concern, you can consider which factor is easier to adjust. Maybe the adjustment of the length is easier, since you can just cut the length, and it's better than to adjust the width of a beam, because you probably need to use grinding the whole side to reduce the width of the beam. So in this case, we are selecting L to be the scaling factor. Therefore, for the rest of the factors, for H, it is a type 1 factor, so H will select to be H3 since the SN ratio is the largest. And for B, although it is a type 3 factors, the influence on SN is very small, but if we don't have cost information, it's better off just choose B3 since the SN ratio is slightly better. Same thing for Young's modulus E, we select E1. But as I mentioned before, if we have the cost information for this level, such as material, if we know the cost of E1, E2, and E3, 3 different materials, it's better off to select a cheaper material, so you can reduce your design cost. The next is the scaling factors. Since you already decided the H to be H3, B3, and E1, the only factor hasn't been decided as the length L. We can adjust L in such a way, move the average to target. There are several methods. We can use try and error and to adjust the length of L and try to find the average output where the spring constant will be 1. In this case, we find out L to be 52, the K will be equal to 1. We want to compare our improvement, and this is the initial design we're given at the beginning, and this is the robust design we obtained using 2-stage optimization. Using the same outer array, we can estimate the SN ratio for our initial design and robust design. As you can see that the robust design will have 26.69. The SN ratio is better than the initial design, 25.44. So we have about 1.25 dB improvement for SN. However, what does that mean for this 1.25 improvement of SN? Let's refresh the definition of the SN ratio, which is a log transformation of the average quality loss. The SN can be represented by -10 times log transformation of MSE. MSE is proportional to the average quality loss. Using the mathematical calculation, you can find out that for 3 dB of improvement in SN ratio, in fact, it stands for you can reduce 50% of your MSE, which means that you can reduce 50% of your average loss. So for your design problems, you can have a rough estimate to see what is your improvement in terms of a mean square, what is your improvement in terms of the average quality loss by look at your improvement. If you have 3 dB improvement, it stands for. So assume you have X improvement and the initial loss is Q INI and the optimum loss is Q OPT. If you have X dB improvement and your loss, optimum loss will become the initial design loss multiplied by 1/2 to the power of X over 3. You can easily using the mathematical calculation to find out the relationship. For nominal the best problems, you can further extend this concept to the improvement of the standard deviation. Since for nominal the best problems, we all move our average output to the target. And their definition for SN is average over a standard deviation square. And because the average is the same, where is the target. So the only difference make for the robust design and the initial design will be the standard deviation. For nominal the best problem, for every 6 dB improvement for the SN ratio stands for the standard deviation of the optimal design can be reduced by half compared with the standard deviation of the initial design. And this is the equation showing this relation. Let's use the concept in the nominal the best design example for cantilever spring. The improvement is 1.25 dB. So the standard deviation for the optimum will be 1/2 over 1.25 over 6, which is 0.87, means the output standard deviation of the optimal design is only 87% of the initial design. Here we are using tolerance delta instead of standard deviation because in the real application, usually we'll use 3 times of standard deviation to represent the tolerance. So they are in proportion. So using this robust design process, we can reduce the output tolerance by 13%. We are using the distribution curve to show the improvement. Assume there are normal distribution for in this design case. As you can see, the initial design, they have K equal to 1 standard deviation and SN ratio to be 25.44. Assume they are standard distributed. We can draw the probability density function for the initial design, which the blue distribution over here. The average is right at the target 1. And the probability distributions for the first stage optimizations is showing here using the black line. Although it does have a maximized SN, however, as you can see, the average output is not at the target, it's at 0.89. So at the second stage optimizations, we are using scaling factor to move our design to the target. And this is the red line showing here. As you can see, the SN ratio is 2669, which is very similar to our first stage optimization result where the SN is maximized 26.7. By using the scaling factor, the SN doesn't change much. By compare the distribution of the initial design and the optimum design, as you can see, both design all center at target k equal to 1. However, for the optimum design, the standard deviation is smaller, which is reduced by 13%, as we calculated from the previous equation.